Hey there, how's it going? Welcome to the Off by One security stream. Sorry for the last minute notice on this one, but had a death in the family, and that's why I haven't been here the last couple of weeks doing these streams. So my apologies for not having anything going the last couple of weeks. I'm working on trying to get some interesting guests on some of the upcoming stream towards, between now and the end of the year. I've got a couple of good people lined up. I just want to confirm that they're 100% a go before I announce who they might be, just to not let anyone down. It's happened a couple times recently where, unfortunately, there's had to been a cancellation, but hopefully that will not be the case. And yeah, thanks. I appreciate that. And as usual, like if I don't have a guest, I like to just go through random things that hopefully you find useful. Give me just one moment. I'm just going to double check my settings and make sure my audio is on the right. There it is. Okay, cool. Just wanted to make sure that that's good. So what am I doing here? I need to, for a particular engagement project thing that I'm working on, refresh my memory with a bypass technique that was discovered by Keen Team, if you've heard of them, as a group of researchers. Um, for the mitigation for Windows isolated heap. That is a mitigation that came out many years ago, going on 10, not quite 10 years, but close to it. And it was a mitigation focused initially on the browser. At the time, that was Internet Explorer, and I don't remember if Edge was out at that time yet, but for Edge as well. And the idea was for allocations that are deemed, I don't know what word to use, but critical, important, some HTML element that they want to protect. They're going to put those in the isolated heap as opposed to the process heap. And forgive me if I stumble or fumble here and there because I'm just trying to refresh my memory as well. This truly was a last minute thing. I said, hey, people might want to see this because a lot of times I do get messages from folks asking for Windows heap stuff, whatever it might be, heap grooming or heap techniques on Windows, because how modern, especially Windows heap allocators work is pretty complex. We started off way back in the day with the standard doubly linked backend free list, and on the front end was the look-aside list, and then we changed over to the low fragmentation heap, and then we came out with the segment heap, and all this stuff is kind of working together, and it's a much more secure heap implementation than it used to be in the past, as you can imagine. Same thing for the kernel. The kernel used to use look-aside lists all the way up to Windows 10. I don't, off the top of my head, I can't remember if look-aside lists are still used in certain situations in the kernel. There's definitely a possibility. I know that the low fragmentation heap made its way into the kernel a little while ago, and that's on by default now as part of the segment heap and the kernel pools, where low fragmentation heap used to be something that was uh, started or engaged, whatever you want to call it, once there was 18 consecutive allocations of the same size chunk. So that was a indicator that this particular chunk size is something that's going to be used quite often, and therefore we should turn on the front end heap allocator so that we don't have to worry about. My voice is all right. Hold on here. Voice is breaking. Let me check something. Give me a moment. Oh, I see what it is. Okay, this should fix it. Give me a moment. Let me let this fail over. So I've got two internet connections, as we all should have. Let me see if this drops me. If it drops me, I'll be right back. Let's see. All right. I should be back now. Let me know if this is better, if it's better, or if it's still the same. I'll wait to hear. Now it's fine. Okay. So when you speak while not presenting. So how's it going now? Is it better? Okay, cool. So I'll keep an eye on that, but it should be good now. So what happened is yesterday my internet went out and my primary connection, which is a gigabit fiber connection, that was the one that went out. So I fail over to my other connection, which is just a standard cable line that it just isn't as strong. So now I'm back on the primary. It should be good now. So apologies for that. Anyhow, if you're just joining in, we are looking at the low fragmentation heap mitigation on Windows that came out probably up to 10 years ago now. The focus for that mitigation was to target use after free attacks, type confusion attacks, like browser based memory corruption bugs that were getting exploited constantly all the time. And the two mitigations that came out, if you've heard me lecture before, you may have heard me mention this, was deferred free or memgc and isolated heap. Those two mitigations were a big they hurt a lot when it came to exploiting browser-based bugs like use after free. And so I need to refresh my memory on this particular technique because I'm working on something that I needed to know. So anyway, I was explaining that. I again apologize for missing the last couple of weeks. I had a death in the family and was busy taking care of things there. So should be pretty solid going forward. And what was I just talking about before you told me that the audio went out? Oh, I was talking about the Windows heaps and the front end allocator versus back end allocator, and how it used to be very simple. The look aside lists. If you're more familiar with Linux, then you're familiar with fast bins, Tcache bins, fast bins. So on Windows, it was pretty much the same, except for look aside lists would hold up to 3 entries per list, and it was all the way up through number 127, bin number 127. And on Windows, it's typically worked where you take the block size, and on Windows, the block size is 8 bytes, and you multiply that by the bin number, and that's the associated bin chunk size that goes into that bin with the relative free list for that bin. Things have changed over the years, as you can imagine. And I was saying that in the kernel now, low fragmentation heap is there by default. So is segment heap. The kernel pools are still there, like the non-page pool and the page pool. And the low fragmentation heap is not triggered anymore in the kernel. It used to be that there would be 18 consecutive allocations of the same size would trigger the LFH for that size request. And there was a ticker or a counter where if you look at a free list, the very first entry on that free list should have a backward pointer that points to the counter. And that counter keeps incrementing every time that size request comes in. And once it hits 18, or 17 and one free, it would turn on the low fragmentation heap to service that specific chunk size. And I've done some lectures or streams specifically on Linux heap, and I talked a bit about Windows as well. But I think we went pretty deep into how the Linux heap works and Tcache bins and how per arena we've got, instead of having a global mutex for one big arena, we've got per arena uh, so each thread would get its own heap as opposed to just its own thread, and it would just make things a lot faster. And you have an associated Tcache bin that was relative or specific only to that specific arena. And on Linux, an arena is just a fancy name for a heap. There's the main arena, and then you can create additional arenas. So anyway, we're not talking about Linux, but the reason I brought that up is because the fast bins on Linux are very similar to how the look-aside lists are or were on Windows. On Windows, though, there was a maximum of, I believe, 3 entries per look-aside list. So once you had 3 entries in that specific look-aside list associated with that specific size, then anything else would go to the backend allocator. And the backend allocator is it's a bit slower to get a request serviced from it. So on Windows, even if low fragmentation heap is servicing a particular size, it would still check in with the base heap, the heap base structure, and check that first. And there's a flag on Windows. If you look at the heap based structure, there's a flag. I forget the name of the member or the field, but if it's a 0, that means LFH is not turned on to service that specific size. But if it's a 2, then that means LFH is servicing that size. And then it goes to the front end, the LFH heap structure, and then there's things like list hints and various bitmaps and such, allowing you to quickly determine what's the most efficient way to service that request. It used to be a very slow process where we were primarily relying on the backend allocator on Windows for the heap. And what would happen is I just mentioned the block size of 8 and then the bins, bin 0 up through 127. And on Windows, you would take the bin number and you would multiply it by the block size, which is always 8. So bin 10 times 8 holds 80-byte chunks. Bin 11 times 8 holds 88-byte chunks, all the way up to bin 127, which 127 times 8 is 1016. That's the chunk size that's stored in that bin. And then anything greater than that, you go to bin 0. Bin 0's got all the other bigger stuff, 1K or greater. And then once you get like above 4K, I think it is, then you're doing a big allocation request. So what would happen is, let's say that a chunk request came in for 80 bytes. So the way that it's organized, or was organized in the backend on Windows, it doesn't make sense to start with any bin number less than 10, because those bins aren't capable of holding a chunk big enough. So let's say you did it the like really slow way. You'd come in and you get a heap alloc request for 80 bytes. You go to the heap space structure and you go into bin number 10 and you check to see if there's any entries in there. So it's a doubly linked free list. And if there's an entry in there, great. You can unlink that chunk from the doubly linked free list and take it. And then the heap would clean up after itself and it would link the chunks that were remaining on the free list together, so we don't have a problem. Um, we've talked about things in the past like double free vulnerabilities and stuff like that as well. But let's say that bin 10 doesn't have a chunk available. Then we could go to bin 11 and say, bin 11, you have 88 byte chunks. Do you have any chunks available? If there's nothing in there, bin 12, that's 96 bytes. And you keep walking forward until you eventually find a chunk that has a available chunk in it. Let's say it's bin 100, that's 800 byte chunks, but you only need 80 bytes. So you would then split that chunk into two pieces, and you would take the remainder and put it in the appropriate bin on the free list, and you would take the portion you need, and you would heap alloc call to return a pointer eventually to that chunk allocation. That's slow. Like, that's really slow to do it that way. So they implemented at some point, like they started with these bitmap structures or hints that basically said, before, like, let's say we get that chunk request for 80 bytes now, we could say, before we go and do it that slow way and start looking at bin 10, do you have anything? Bin 11, do you have anything? Bin 12, so on and so forth. If there was a bitmap that indicated whether or not there is actually an entry in the associated free list with that bin, we know whether or not to even bother executing additional code. So it's going to be quicker to just check this bitmap if there's something that exists there, than it is to do it the slow way. And at some point along the line, they changed it to where it used to be the doubly linked free list on the back end, the forward pointer, the very last chunk on that free list, like the very last one, where does its forward pointer point to? There's no further chunks on that list. So it used to just point back to the Sentinel node, and I've shown this on Linux before, as where the Sentinel node in the main arena structure would just simply have a pointer back to the first chunk on that doubly linked free list. And then the very first chunk on that free list backward pointer would point to that Sentinel node, which would point back to the last chunk on that free list. Then they changed it at some point along the line to where the back pointer pointed to that LFH thing I talked about, the little counter that said if you hit the threshold of 18, then turn on LFH to manage and service that chunk size. And then the very last chunk on that free list, instead of pointing back to the Sentinel node, could point to another free list, so that it would be faster to just keep walking to see if you can find a chunk that's available. I'm kind of stating it from a high level here. I'm not getting into the technical details, but that's kind of how it worked in a high level. And the whole purpose that I've explained as well in the past behind a front end allocator versus just having a back end allocator is for speed optimization, where it takes less code to execute getting an allocation from the front end allocator if there is one available. You might say, well, why don't we do it all the time? Because there's a problem called fragmentation. The more fragmentation that exists on the heap, it's just going to get messy, right? Same thing with a hard drive. If we're automatically defragging all the time, there's a rule on the heap, and this applies to most heap implementations across operating systems, that no two free chunks of memory on the heap are allowed to be side by side and free. You would coalesce them. The heap free function, or free on Linux, there would be some checks it would make, and it would determine whether or not one of the adjacent chunks in memory to the chunk we're freeing is also free. And if that chunk is also free, we would merge them into one big chunk. There's little flags there that get checked to state whether or not the previous chunk is in use, or the next chunk can be checked as well to see if it's in use. And that's what those flags are there for. So if we if we have this rule that says no two free chunks are side by side, and it's automatically getting cleaned up each time heap free is called, then we don't have to worry about fragmentation as much. But think about what's happening there. The code execution, the stuff that has to be the code that has to execute to merge or coalesce those chunks into one is overhead. So if we have to worry about fragmentation and cleanup, it's going to be overhead associated with that. It's going to be slower. So we have this concept of a front end heap, where the front end heap, we don't worry about fragmentation when it comes to the front end allocator. And the reason we don't worry about that is because traditionally it was supposed to be chunk sizes that are popular, that are constantly being used. And I've given examples in the past where if you take something like a browser and you look at a website like CNN.com or whatever, and you look at the HTML, you're going to see a ton of span elements, div elements, table elements, buttons, TR, TD, all kinds of HTML elements that are very common. So if you're using something like a browser and you're navigating different websites, there are going to be HTML elements that are constantly being used. Well, those HTML elements have a static size associated with them. So when you go and look at the class, the C class or C++ class that is associated to something like a button. So if you were to look at it, there would be a C button class, colon, and then you would have create element, scalar deleting destructor or vector deleting destructor, and you would have all these different member functions or methods associated with that class. Inside the create element function, there's going to be a call to heap alloc, and there's going to be a static size associated with that specific element. That's just the way it is. Now, if you're thinking about something like the inner HTML of something, say you've got a button on the screen in a browser window, and then there's text and it says, click me or button. That is a separate allocation from the actual button element itself. That button has a static size. The inner HTML or something else or an attribute of that specific element or object has a completely separate allocation associated with it, and that may be variable size. So the reason I'm saying this is because since those certain objects are static in size and very popular, it makes sense to let the front end allocator service those requests, because we don't worry about fragmentation associated with that specific size because we know it's constantly being requested. So that should make sense, right? We don't worry about fragmentation when it comes to sizes that are constantly being requested, because it would actually take more code to like just constantly defrag and put them into the back end free list as it would to just leave it in the front end, because we know it's going to be requested coming up soon. And then other mitigations and changes they started to make along the way, and this again applies globally to all heap allocators for the most part across operating systems. They started doing things like randomization. It always used to be last in, first out, typically, because last in, first out is faster than random allocations. I think I did a session in the past where I talked about Jason Evans Malik, J.E. Malik, where he got hired at Facebook to go and do some things, because I remember one uh, meeting or presentation, I should say, that he did from Facebook, where he said he was able to get a 3% performance increase or enhancement based on a particular decision or technique that he applied. And it had to do with page purging, dirty page purging, to where if a process is being gluttonous or greedy and it's got a lot of memory committed to it from the kernel that it doesn't need, or maybe it needed at one time when it was busy, but it doesn't need it anymore, that there should be a way to purge those pages and give it back to the kernel so that it can use it for other processes running, so that we don't have to spin up another uh, VM or whatever, another resource. So The decision that was made to get that 3% performance increase took a security hit. So it was a situation where performance was given the precedence over security in that case. And that's how you get that performance. Because in order to be able to do the page purging in the way I just described, you you would need to not do random pool allocation or random heap allocations, because that's what's going to allow you to push the dirty pages that are clean now, that have no longer have an allocation actively on it, down in a direction where it can be purged. So again, security versus performance, and those decisions again factor into the overhead. So random allocations from the heap free lists is going to make it more difficult for deterministic properties that we like, or it's going to make it more difficult for me to groom the heap so that I can line things up the way I want. I mean, think about something like a use after free vulnerability. Think about a use after free vulnerability where an attacker is intentionally causing a object to be prematurely freed, typically by decrementing its smart pointer counter to 0, and then running a garbage collection like in JavaScript so that it gets given back to the heap manager so that it can be reallocated. That is how we're able to, in a use after free situation, exploit it easily, because last in, first out means if I just got this object prematurely freed and I immediately do an allocation of that size, I know it's going to be that. It's going to be the object involved in the use after free that I want allocated back to me so I can fill it with something harmful like a V pointer that I control. So if we randomly allocate from that free list or heap, then I'm not likely to get the object. I'm not the object. Well, it was an object, but the object that got prematurely freed, I'm not likely to get that returned back to me in my heap call. If it's randomly being allocated, I'm not likely to get the one that I want. And the one that I want is the one involved in the use after free. So that random allocation is going to increase the security. Now you could think, well, can't you just do a bunch of allocations and flush the free list? And then you know that you would definitely have filled what you want to fill. Yeah, that stuff works. That gets into heap grooming a bit. Heap grooming, though, in modern times, you're more thinking about stuff like, and it still goes back to the old techniques that I think like Alexander Sotorov and others disclosed back in like the late 2000s, like heap feng shui. And there's techniques like the plunger technique, where it's a silly plumbing term, obviously, and you're essentially flushing the free list so that there's no more entries in there. And then if you do a bunch of frees, you know that the stuff that you just freed is what's going to end up in the free list. And you can do this multiple times. And like if you're making a bunch of allocations, you're trying to, in a position independent way, know what's in the relative area where you're doing your exploit. Like obviously with 64-bit ASLR on, we have no idea where we are in memory. But if we can get an address and we can start doing allocations and frees and such, we are going to know that relatively to where we currently are in memory, we control what's there, or at least we hope we can control what's there. So all this stuff comes factored in. And again, those are the decisions that have to be made when you're designing something like a heap allocator. It's always that security versus performance thing. And like if you're on Linux and you've got PHK malloc and PT malloc and JE malloc and TC malloc, thread cache, like there's a bunch of them out there and they all do things differently, um, because some of them are focused more on performance. Because the idea would be like, if I've got this custom heap allocator running in my data center deep in the core network, if someone's able to actually exploit the fact that I am prioritizing performance over security on the heap allocators deep in the data center, if somebody's able to get there and actually exploit that behavior, we got bigger problems, right? So how did somebody get to that point? So that's when you can start making some sacrifices from the security side. Okay, so that's enough ranting there. So what just asking this exploit automated, right? I'm not sure what you mean. Do you mean like the technique around heap grooming isn't automated, or what do you mean? If you elaborate, I'll happily answer the question. So I wanted to give a little bit of background there because what we're specifically looking at or we're about to look at now is the isolated heap bypass technique that was discovered by Keen Team many years ago because it's a really neat concept. So back in 2014, when deferred free came out and isolated heap came out, it killed a lot of the use after free vulnerabilities. But then people discovered bypass techniques. And for deferred free's first implementation was really weak. They changed it and updated it and called it memgc. And memgc was really effective. That thing killed 90% of what should be exploitable memory corruption bugs in the browser. The difference between deferred free and memgc, deferred free being the first iteration, is deferred free did two things. If my memory is correct, it set a threshold of 100,000 bytes, and the idea was, I'll make a silly analogy. In the United States, you have to be 16 and a half years old, I think, to get your driver's license to be able to drive a car. And I remember when I turned 16, I assumed that my parents were going to be just as excited as I was to go to the driving test and get my driver's license. And of course, I heard the typical driving is a privilege, not a right, and that whole thing, right? And it's similar concept here with deferred free, where it says there's a threshold now. Just because you are a chunk that has been your smart pointer, if relevant, has been decremented to 0, and you are now available to be given to the heap allocator for reassignment. So you're given to a free list and you are now available to be reallocated. Just because you're in that position doesn't mean we're going to put you back into production again very fast. We're going to wait until 100,000 bytes is queued up, needing to be flushed out and given back to the heap manager before we do that. It's kind of a silly, it was a silly one, right? Because think about that. The idea is if I'm an attacker and there's a use after free vulnerability, for example, my goal is to prematurely free this object so that I can immediately reallocate it. Last in, first out. I want to allocate something of the same size as the object that was prematurely freed so that I know what I want to be stored there has been stored there. So the idea with deferred free was, well, if we don't actually free those things until there is queued up 100,000 bytes, that attacker who wants to fill the slot of the object involved in the use after free isn't going to get it returned to them because they got to wait until the queue is met. So if you were to think about that, what might you try to bypass that protection? How about we do an allocation of 100,000 bytes at the same time and immediately free it right when we get our object to prematurely free? That's going to meet the threshold of 100,000 bytes. And now when we do our allocation, it immediately gets returned back. Like that was a dumb technique or protection. Like that's the other thing that deferred free did was it checked the stack, the thread associated with the object that's being freed. It checked its stack to see if there's any active references to the object that we are freeing. But that ends up not really being enough because it's just not. What they failed to do that they fixed with memgc is they also check all the other objects that are currently in use to see if any of those objects have references to the object being freed. Because if there's still active references to the object being prematurely freed, there's a problem. There's going to be a situation where we go to access that reference, and the reference is going to be to freed memory. If it's freed memory, by the time we go to use it, it's going to crash the process because it's going to see that the memory you're referencing is freed. If that memory has been reallocated, then the reference is going to work, but what's there might not be what's expected. What if it's a different data type? What if it's a different, just different data altogether? It was pointed to a V table, and now it's pointed to some random string. There's probably going to be a crash at that point. So memgc really hurt the ability to exploit memory corruption bugs in browsers when that came out. And then there was isolated heap. Let me check the questions real quick. How you managed to learn all this in 20 minutes, almost 80 days learning Windows? It's been almost 80 days learning Windows memory threads, and I find it difficult to understand. 80 days? That's no, you got a long ways to go. Like you probably learned a ton in those 80 days, and you just got to keep going, right? I'm a lot older than 20, so it just takes time and repetition. But you'll totally get there. Uh, cool. So the other one, isolated heap, that's the one that we're working on. But what's funny is in this exploit I'm about to show you, we had to bypass deferred free. And you'll see the 100,000 bytes being allocated and then freed to get around deferred free because it was a really weak protection. Isolated heap is the other protection. I explained a little bit about it. This first came out before Windows had any sandboxing in the browser process. So other browsers like Chrome had proper sandboxing in them, and Internet Explorer at the time did not. And so this was a mitigation that was supposed to help with that. But even aside from sandboxing is different, right? I'm talking about heap allocations and the fact that certain objects should not be in the same pool with other objects. That's what we're looking at. So critical deemed critical objects need to be put in isolation away from other allocations that could hurt things. So that's what I'm going to explain here. So they basically made it where the majority, if not all, uh, HTML elements, again, span, div, table, button, HR, those are all put in an isolated heap, but it's a single isolated heap. It's not multiple, it's one isolated heap. You're either in the isolated heap or you're in the process heap. Windows used to have it where everything was in the process heap. I mean, that's most OSs, but everything was in the default process heap, and the process heap would just keep growing and growing and growing. Um, as much memory as you need it. The heap spraying worked really well back on like 32-bit, right? Because it's just default process heap, and you're just growing it to get out to predictable addressing, even if ASLR is on. So now we know that critical or just HTML elements are going to go into a separate heap from normal allocations. What's an example of a normal allocation? A B string, a JavaScript string. That would be an allocation that gets put somewhere different than the isolated heap. That's going to go into the process heap. So let's look at the exploit code real quickly. This VM you're looking at, it's a Windows 8 box, and it all these things that say testing 12, testing 10, those are all my old browser fuzzing farm back when I was really heavily exploiting browser use after free bugs because you got paid a lot of money. This was a VM member of that fuzzing farm. So those testing are mutation numbers. And I had a controller that would I've explained this in prior streams where I would take any use after free type confusion or any other memory corruption bug against browsers, I would put it into my mutation engine, we'll call it, which that's a fancy way of saying some code that was duct taped together. So you would feed the mutation engine, just like think of AFL, the American Fuzzy Lop, right? Or any other good fuzzer. It needs a valid source file from which it mutates, right? So it's going to take, like if you're using AFL and you're going to fuzz something that reads PCAP files for sniffer captures, then you need to give it a PCAP file with the stream or protocol types that you're targeting against, whatever it is you're targeting. Like if you want to find vulnerabilities, fuzz Wireshark, you will find vulnerabilities if you do it well. And you've got to select different packet types. Like you might say IPv6, I want to start fuzzing that. So, okay. Or I want to specifically mess with IPv6 encapsulation types. Like remember when IPv6 first came out, there was a lot of tunneling technology that came out because we had to make it so people could migrate over to IPv6 a little bit at a time. So you could encapsulate IPv6 on IPv4 networks or vice versa. And so you could choose that as your target. So you would give AFL a PCAP file with packets in it that use that protocol. And so the protocol parsers, just like file parsers, file format parsers, it's going to go through the verification or validation routines are going to go through, and you're trying to exploit and mutate, looking for vulnerabilities associated with like metadata stuff or like delimiters and different things. So that would be giving a seed or sample file to the fuzzer so it can mutate from that. This, what I'm talking about is you need to teach the mutation engine all of the different browser features supported by that browser. So a browser like uh, Safari or Firefox is going to have different features it supports than Edge or Chrome and vice versa. So you need to teach it about the features supported by that browser, and you need to teach it JavaScript really well. So when you look at a use after free vulnerability, the the actual JavaScript code that is causing the use after free is pretty nonsensical in most cases. It's a bunch of allocations and it's a bunch of frees and it's a bunch of like appending child node to something and just doing weird stuff, clearing out the inner HTML, causing errors and handling the exceptions. And um, it doesn't make any sense, but for whatever reason, that specific order of JavaScript code is causing a crash. And you need to be able to determine why. And so what I'm about to show you is a use after free vulnerability that is being triggered. It's crashing. Now, if you were to exploit this vulnerability or even just cause it to crash without a bypass for isolated heap or deferred free, then you're going to get a different result and you're not going to get the result you want. Like, for example, let me just open it real quickly. I said this would be short and I clearly lied because I gave too much background. Um, so this is the top here. Let me zoom in a little bit more. It's obnoxiously large, but that's so you can see it online, of course. For whatever reason, StreamYard just does not like to do HD streaming. So this function up top is called collect garbage to, which is weird because we normally only see collect garbage, like down here at the bottom. Collect garbage is a real JavaScript function, right? It's supposed to go in and do some cleanup on the heap to see if there's any objects that should be like returned back to the manager to be reallocated. So collect garbage is normal. We typically run that at the end of certain types of browser memory corruption bugs to force cleanup. And so collect garbage 2 is a function that was intentionally created to get around the deferred free threshold of 100,000 bytes. So I want to try something real quick. I'm going to change this value from 100,000 down to just like 100. So now it's just 100 bytes. And I'm going to save that. And we are going to run it. So that is this right here. It's called isolated heap bypass. I double click it. Let's see what happens. So it says allow blocked content, allow it, and nothing happens. Let me refresh it. Refreshed it, nothing happens. I'll close it, try it again. Nothing happens. Why is nothing happening? Because we're not bypassing deferred free, so the exploit is not working. What is really happening is we are actually freeing prematurely. You can't see this, but I'm telling you, the exploit is prematurely decrementing the smart counter pointer for a particular object to 0. That is then being made available to be given back to the heap manager, but it's not being given back to the heap manager because the threshold is not being met. So it's still sitting there waiting for a threshold to be met, so it's given back. So the attack that's happening after what's supposed to happen is we're supposed to get that object returned back to us during an allocation so we can exploit this thing. We're not getting that object back. So therefore the exploit is failing. And because we don't fill that object that we want to fill accordingly, it's just silently failing. It's not crashing the browser at all. Everything's fine. This would be a situation where there is a bug that's not being seen because we're not doing things right. But in fact, it is actually working. The problem is that object has not been given back to the heap manager for reallocation. So the allocation we're getting is the wrong one. Where now if I go back in and I change this back to 100,000 bytes, so now it's back to 100,000. I just saved it. Watch what happens now when we run the exploit. It should crash. And bam, it crashed. So look inside. Let me bring up a zooming thing here. This is old box that's in the middle of two boxes. So what is the command on this thing? Magnifier? Yeah, magnifier. There we go. So got way too many computers here. What is going on? Okay. So now I'm going to zoom in and you can see that EAX holds 42424242. The exploit is working. We should not be able to get that value. I didn't even tell you where it's coming from yet, but into the accumulator register. It's there now because the deferred free bypass worked, because that 100,000 byte threshold has been met and the object involved in the use after free is actually being freed and being given back to us in our next allocation, allowing the exploit to work. So the only reason I really wanted to show you that portion is because it shows you how bad deferred free is, how deferred free is not a good mitigation at all. All right, so let me close this. And let's go back to the exploit here. So that's what that does. If we scroll down, this right here, what's happening up here, like this down, this is all part of the isolated heap bypass that Keen team came up with. I'm going to draw out what it's doing because it's hard to visualize if I don't. You can see though at the top, var junk equals new array. We're allocating memory, right? And we're calling this variable junk. Then we're going into a little for loop and we're allocating 4 objects. You can see in that line right here, what we're creating are title elements. Title is an HTML element, and we're creating 4 of those through that little for loop, and it's an array. So we've got index 0 to 3. That array of title objects is going to be adjacent in memory, and we're going to leave it there. The reason why we're creating that is to prevent coalescing on the backend heap. So this exploit actually involves the backend allocator, and we are creating that array to prevent coalescing, because if coalescing occurs, it'll break this exploit. Now, the next thing that's happening is we're creating yet another 4 title elements, and we're calling them title. So we've got a second array, 0 through 3, title elements adjacent in memory. So I'm going to draw that out real quickly in Paint. All right, let me expand this out, get my drawing thing. This isn't going to be pretty, but at least it works. It's something. So let's pretend that this is the heap, the isolated heap, in fact. Now, if isolated heap wasn't on, we wouldn't have to do this part. It'd be super straightforward, but isolated heap is on. So what just happened then is we created somewhere on the heap, we have no idea where we are, it doesn't matter, 2 arrays of 4 title elements. So I'm going to say that the one on the left is junk because that in adjacent memory, that would be the order because we created this one first. So junk. And then next to that is title. You can't see point. The point did not show. You can't see what I'm drawing? Oh, paint's showing now? I'll just wait one more person to confirm. So can you see what I've drawn? And it takes a while. I've said this many times on the stream, like for whatever reason, it takes time for the comments that you type in to show up on my view. So Hussam says yes, no. Numi says no. I'm confused. Oh, I know what the problem is. I am not sharing the screen. I am sharing VMware, and you are not seeing it. So whoever said they could see it, get off my computer, right? So let me fix this real quick. Let me actually try this. I'm going to go into Windows 8 here. I'm going to bring up Paint inside here. There's Paint. And let me see if I can pass through this drawing tablet to the VM. I'm not sure if it's going to let me, but we'll try. Connect. Let me see if this works. All right, I just passed it through. Let's see if the drivers recognize it. All right, it's working. Now you should see drawing. All right. So I am going to start drawing what I was just drawing outside of that screen. So here is, let's pretend that that big long line or that big rectangle is the heap in general. And then I'm going to create 2 arrays. So the one on the left is going to be called junk. And the one on the right is going to be called title. And inside there, we had 4 title elements. So let me just create them. All right, so now I've got my 8 elements, and I'm going to say the index on the left, we've got 0, 1, 2, and 3. Same thing on the right, 0, 1, 2, and 3. Now, right now, they've all been created. We created new memory. They've been allocated. So I'm gonna make them all red because they're all in use. So now let's go back over to the code. After we've created those 2 arrays, look what happens down here. It says title index 2 equals null. We're freeing that specific title element. So if we go back to our drawing, that means we would choose green, go into the title element, offset 2. So that one is now free. This is happening before we even start the actual use after free exploit code from running. This happens first, and it's by design. And what we're doing is making space in the isolated heap for our object involved in the use after free. So again, these 2 arrays of title elements that we've created are happening first, and they're being allocated in the isolated heap because that's where elements go in HTML in the browser. So we've intentionally allocated this, and right now we've punched a hole. So imagine we're punching a hole, and the size of that hole is exactly the size of the object that's involved in the use after free. We want the object involved in the use after free to use that specific chunk. Make sense? So we've set up the environment intentionally freeing an object of the size of the object involved in the use after free because we want to know relatively where that object's going to be. And that's how we do it. So it's pretty neat, right? We're controlling where the object's going to be that's of interest to us. So let's go back to the code here. Give me a moment. Now, if you look down further here, I'm not going to go through everything. Like this code here is all the code involved in triggering the use after free. Like I said before, most of the time, not all the time, but most of the time, use after free vulnerabilities are pretty nonsensical as to why it's happening. Like you can get into the low level details as to why it's happening. If you're a developer, that's what you would need to do to fix the problem. I demonstrated that in a prior stream at one point. Like I went through and I set a breakpoint on the reference counter associated with the object involved in the use after free. And each time the reference counter was being incremented or decremented, we hit the breakpoint, and then we could look at the call stack at that moment in time, and we could see what's happening. And we could also use the math atan2 function in JavaScript and set the corresponding breakpoint in WinDebug, and we can see exactly um, where we are in the JavaScript code execution, like literally the line number in our JavaScript where we are by setting up those breakpoints accordingly. That's going to allow us to determine why this exploit is possible, why the bug is there, like what's causing it. We don't usually care about that though. We're just trying to hack it. So who cares? From the exploitation perspective and finding these vulnerabilities, typically the JavaScript that you see like highlighted on the screen right now, it doesn't make any sense, meaning no one would ever write this JavaScript in any production environment. Like it doesn't make any sense. It doesn't do anything. But it's because of this unorthodox, weird code that a use after free situation is manifesting and being triggered. So we're not going to go into the detail of that code that has been highlighted. If you care about that, go look at one of the prior streams I did on browser exploitation, and I go into detail on that stuff as to what this code's doing. What I care about, though, is the fact that that code is causing a object to get prematurely freed. And I know the size of it, which is why we created those title elements inside the isolated heap. We know that we punched a hole. I said before that that hole is where the object we care about is going to be. And then now we want to bypass and use what we've set up at the beginning to bypass isolated heap. So look what we're doing here. Title 0 equals null, title 1 equals null, title 3 equals null, and then collect garbage 2, collect garbage 2. The reason for the collect garbage is because at this point, the object involved in the use after free has been freed, but it's not yet been given back to the heap manager. I showed you that already. Remember, I changed that allocation from 100,000 bytes down to 100, and it didn't crash in the browser. And then I changed it back to 100,000, and it crashed. That's because of this right here. We've caused the use after free. The object is now freed, but it's waiting. It's waiting for the threshold to be met. That's how we're forcing the threshold to be met, is those collect garbage 2 calls. But before that, we were freeing title 0, 1, and 3. So if you go over to our drawing, what happened between the start of the code and where we are now is this object that I just colored blue was allocated and used by the object involved in the use after free. And then it got prematurely freed due to the reference counter decrementing to 0 with the C++, the way Microsoft did the C++ smart pointer implementation in an invasive manner is kind of weird, but I talked about that before as well. So now we are intentionally freeing 0, 1, and 2, and we are leaving the junk title array in place to prevent coalescing, because that would break our attack. Now we've got 4 title elements side by side and freed. What's going to happen? It's going to coalesce. So those 4 objects in the isolated heap adjacent to each other, they are going to coalesce and become one big chunk. So let me just visualize that. So I'm going to delete inside here. And we're just going to color the whole thing green now because now it's one big chunk because of the coalescing. One big chunk. Okay, great. So now we go back here to the code. We do the whole collect garbage thing. Great. Down here, we are now allocating some memory called area. And you see another for loop. Inside this for loop, we are creating a bunch of area elements. So area is another HTML element. And after we do that, we are running another for loop, and we are referencing our area object, and you can see, messing with the attributes. We're saying, I want this area object to be the shape of a rectangle, and I want the coordinates of this rectangle area object to be as such on the right. So look at these coordinates. And there's intentionally four of them side by side. Well, if we take this number right here, which is supposed to be the coordinates, and we put that into a calculator, watch what happens. It's 42424242. See that? So if I say, get rid of that, decimal, paste that in again, go to hexadecimal, it's 42424242. You saw that come up in the debugger quite a while ago. So that's where EAX is getting that 42424242 value. So how is this working? Well, what's happening is this drawing here, that big coalesced area of memory called title, or was called title, has been freed. It's now been reused by the area element for loop, where we've created a bunch of area objects, and then we've set the shape of each of those objects to a rectangle, and we set the coordinates as such. Now, here's the tricky part. This is the part that would take a lot of debugging to figure it out. Like, we're kind of cheating and looking at the Martha Stewart style of like it's already baked and finished. But let's go back to what it used to look like that. The object involved in the use after free is this one here. Now, when you look at a C++ object, and if you've seen me talk about this before, my apologies, but you can't ever get enough of this, right? Let's see, expand that. And if I create a C++ object here, let's just pretend that's an object, and I'm going to name it as such. It's got, because of the way Microsoft did the smart pointer implementation, which is a weird choice. I still don't know why they did it this way. Someday a developer will tell me from Microsoft from way back in the 1990s, I guess. At the top of the object, because of the way Microsoft did smart pointers, you are going to have a V pointer first, which is the virtual function pointer, followed by the reference counter. Now, the reference counter, when this object gets created with create element, it's going to get the reference counter set to 1. And then as objects add references and release references, those are the two function calls that get called out of each class. There's a member function called addRef, and there's another one called release. That's going to be what increments and decrements the reference counter. If it gets to 0, that's when it gets marked as freed. And so the V pointer, when the object first gets created, it's temporarily pointing to a virtual function table that has nothing to do with what type of object it's going to become. It's almost like, if you're familiar with medicine, like a stem cell. A stem cell comes out of the bone marrow and it gets marked where it's supposed to do some specific thing. It's told to do something. So when this allocation occurs and the object gets put into use, it starts off as kind of like a shell object, and then it immediately gets told what it's going to become. So the V pointer is then going to change from pointing to a generic V pointer to the V pointer associated with the class that instantiated this object. So it's not to scale, obviously, but just pretend that what I'm drawing here is a big table full of pointers. And these are all the member functions. So, like, dumb example, if you're not a developer, let's say you want to create a dog class, and you want to have the ability to create instances of dogs. So if you can create dogs, you can select the breed of the dog and the gender of the dog and the color of the dog and all those things, right? Those are the attributes. And then there's the member functions like sit, speak, roll over, lay down. Those are going to travel around with this object. So if you instantiate an object and you call it Fluffy, then you would say Fluffy dot speak. And if virtual function tables are being used, they're not always used. Depends on what it is. Virtual functions, if you get like class inheritance, and anyway, I'm not going down that rabbit hole, but you would have those member functions, and you could access them. So what we've done in slot number 2 in title is in there right now is this object and or its attributes. And I say and or because you got to debug it to see where things are ending up. Like that's when it gets hard. And I did a browser exploitation stream a couple months ago, and it was on information disclosure, if you remember, if you were there, and it was about memory leaks and how you could leak out an address, and that's how you would bypass ASLR. It's part of your exploit chain. You've got to have an information disclosure vulnerability. You need a remote code execution and info disclosure at least. So the one I demonstrated was that, and we went through how you would go about debugging to see what ends up being there, what ends up being created, because when you are massaging the size of the allocation, when that allocation is freed, different things are now going to be capable of using that memory up. If it's too small, certain things can't use that memory. So if you make it big enough, something meaningful could show up there. And that's how we were able to leak out certain virtual function tables that or we were able to leak out pointers within a DLL that was meaningful, that had enough ROP gadgets in it for us to do our exploit. So that's go watch that stream if you want to see more of that. So what I'm trying to say here is this V pointer that ends up, and I could be misspeaking, this could actually be like an attribute of something, but we're intentionally lining it up so that the use after free object that fills this slot ends up getting this 42424242. Like, it lines up so that what's right there is going to be the 4242s, right? I'm not going to draw anymore. You get the point. Like, because what happens is when the reference occurs to this object, it's going to dereference the v pointer from the object. I've drawn out this code in the past. You would have code that would say something like move into Rex dereference register 14, right? And if register 14 was the object pointer, if we execute this code right there, the v pointer is going to get dereferenced out of it, and now we've got a pointer to the supposed virtual function table. But because we're able to mesh this as such, what we got to store at that precise location is 42424242. So what's being dereferenced out of the fake object is that value. Now we control memory, because oftentimes the next thing that's going to happen after that code executes is we're going to dereference a virtual function pointer from the virtual function table. We would say something like move into RDI and then dereference racks plus some offset like 8. That's going to grab from the virtual function table 0, 8, 16. Like, it's going to grab that one right there. So we're dereferencing this virtual function into RDI, a pointer to it. And then we'd see something like a call RDI. Now, something like control flow guard is going to probably protect this. So you'd have to find a uh, a ROP gadget that's within an appropriate bitmap entry inside the control flow guard table that allows you to do the bypass for that too. You've got multiple things here. So that gets quite technical, especially if you don't do much on heap exploitation. But that's what's happening. And as we saw when we run this exploit code, that's why we're able to see in the debugger here, 42424242 show up in this case the accumulator register, because IE11 in this case was a 64-bit process, but the actual browser windows were only 32-bit. That's why that's working. And you saw before when I changed the deferred free bypass from 100,000 bytes to 100, this didn't happen because we never met the threshold. So the object in the use after free was never given back to the heap manager. Exploit fails. Now, just to show you one more thing, if we go in here and we say unassemble function, let's just choose one, MS-HTML, bang, C button. So C button, and then the member create element. Now, what's going to happen is we're going to see a heap alloc call. Give it a moment. It's still disassembling it or per window. Why are you taking so long? Hopefully this finishes up here in a moment. Couldn't resolve. Do I not have my, oh, I have a space in there. I don't know how that happened. Let me fix that. There we go. Now we run it, it should work. I was about to reload my symbols there in a second, but I caught that typo, thankfully. Or maybe it doesn't want to work. There it goes, it worked. So if we scroll up here, you can see right there, isolated heap is being loaded. So when you make a call to heap alloc, it needs the heap base pointer. It needs also the size argument, and then probably a DW flags argument. So you're seeing that with this call to the C button class, that button will end up in the isolated heap, versus if you do something like, let's look at a different allocation type. So if we say unassemble function, MS-HTML, and then bang, what's a good example? C string, CSTR, and then colon, colon. Let me see if I can find it. I got to parse through the symbols real quick. Hold on. I don't remember what the function's called that I'm looking for. So I'm asking it to show me, and it's not doing it. Hold on here. There we go. Geez, that took a long time. So C string, append, realloc. Realloc might work. Set equals, hold on, let me find vector deleting destructor, free. Free probably would have worked too. Alloc, there we go. Underscore alloc. So if I run that, unassemble that function, what I'm hoping to see is a call to the process heap instead of, not call to, but the loading of the process heap instead of the isolated heap. And that's important because in another stream, I showed you that if you find a use after free, or depending on the browser, if you find a use after free vulnerability associated with a string allocation, then it's not going to be protected by, potentially not going to be protected by isolated heap the same way. So right there, see how it says G process heap and not isolated heap. So stuff like that's important to note. All right, so that is the end here. Let me see if there's any questions I missed. Great explanation. I learned 20% of the lecture. Good. Yeah, you got to watch this stuff again. End day weaponized exploits take advantage of patch vulns, but not update the recent version by the user. What does you set to free target? Wait, end day weaponized exploits take advantage of patched vuln. I mean, use after free, it could be either, right? If you find it and there's no patch, then that's going to be a 0 day. If you do a patch diff or something and you're able to find it after the patch comes out, then that's going to be an end day vulnerability. The end being the number of days it took you to find that, right? So it's, to be honest, if you said you've been learning Windows stuff for 80 days, don't hurt yourself. Yeah, 80 days that's just at the beginning. Don't push yourself too hard. All right, so I don't see any other questions. I'll hang out for a couple minutes though. If I missed something, please post it up again. Thanks for joining the last minute stream here. I appreciate it. I will hopefully be more organized for next week and get something set up in advance so you know what it's going to be. But other than that, have a great weekend. and I'll just stick around for another moment to see if any questions come up, but I'll just drop off after that. But it's cool. I mean, that's a neat technique, bypassing isolated heap and deferred free. I remember MemGC came out, and there's no good. I've never seen a bypass technique for MemGC. You just have to avoid it. Like when it's there, you're stuck. Cool. Yeah, thanks. Appreciate it. A community? You mean by like a Discord channel? I probably do need to set that up. It'd be cool to like have stuff persist instead of just in these chat windows. Yeah, exactly. I'll do that. I'll set up a Discord channel, and that way it'll be good to kind of carry on conversations and stuff like that. So I'll take a note. All right, great. I'm gonna head out. Again, have a great weekend, and we will see you next time. This will be on YouTube, of course, after this, so you can rewatch it.